Welcome to the 21st of April Dallas Personal Robotics Night Virtual. Here we are in the middle of a pandemic when the country's trying to open, but people keep dying. Well, we're going to be online here, and we're going to make good about it. So tonight we have a handful of folks. See them on the screen to the right there, I presume. So if we just walk through quickly, we have a couple of demos already. Actually, I think I'm sharing that on the presentation here, right? So if Murray comes, I know he's going to want to talk about PID loops. Mike is here and has a claw machine to demo. I have a demo of a SPI communication between Raspberry and Arduino Mega. Does anyone else have anything they'd like to kind of like demo before we just start talking?
I don't have a demo, but I have a show and tell.
A show and tell. That's okay. Doug, show and tell. Anyone else? Okay. Then what we'll do is I'll stop presenting, and we'll just go down. Oh, good. 7 Photons has the LiDAR tracking. That would be Jack. Awesome. Okay. So, well, let's just walk down the list then and talk about what we did in the last week. With so few people, I think we can just do the demos while we're in the middle of it. So, Jack, looks like you're first in the list. Would you like to take it away?
All right, sure. I finally got the competition robot wired up, and it doesn't do much right now, but you can see the LiDAR sensor tracking the wall. There. Can you guys see the blue light?
Yeah.
For a moment.
Okay, so that's pointing to the wall, and as I rotate it, it rotates with...
Okay.
It's pointing to the wall.
And I'm hoping to use that so that I can tell its orientation in the competition. Wait, did it? Oh, yeah. It seems to be pretty accurate. I think the max angle is that it's usually off by is about 5 degrees. So we'll see if that works.
That's pretty cool. Are you looking to use the Scott Gibson approach to locate using the walls?
What approach is that?
I think he would use the spinning LiDAR like that, and he would find the angle at which the return is the shortest, and assume that he was perpendicular to the wall.
Oh, okay. I don't think that's exactly what I'm trying to do. I'm just trying to kind of set a point that it watches, and that, or on the wall that it watches. And then as it moves around, it keeps pointing in that same direction so that it knows where it's facing.
Yeah. Okay. Well, that's pretty cool. Looks like good progress.
Yeah. Hopefully I should get to work on it more now.
Is school winding down so you have more time?
Not yet, but it's about to end soon, so...
Okay, well, thanks. Next in the list, we have Mr. David. Do you have anything this week?
Am I Mr. David?
Yes.
I'm gonna take my shoes.
Hey, Lila.
Are they self-walking shoes?
Don't smell that thing. You'll probably pass out.
I'm putting them in air cooler mode.
Okay. Have you been doing anything interesting this week, or just dawdling around at home?
I've been doing yard work.
Oh.
A lot of that needs to be done.
My yard looks better than it's looked in at least 20 years.
It's been nice weather for it, so that'll get you out too. That's cool.
I think it's supposed to rain all day tomorrow, at least here in Denton.
Yeah. It'd be a good day to be in.
Is Kareem here?
He is.
Yeah.
I was just reading your email about, oh, hey, video, hooray.
I exist. Yeah.
You're not just a disembodied voice.
I normally
Well,
try to be, but yeah.
I was reading your reply to our new friend from New Zealand, and I just read it, and it's good questions, and I think you nailed it in terms of trying to define exactly what it is he's attempting to do. I was not clear enough, and I was not clear enough on what his goal was to understand what to suggest.
Yeah, that was sort of the trouble I was having too. I also didn't have the context of, I think I missed his presentation last week and whatever, or the one before. So I wasn't familiar with his robot either, and I was just going from the description in there. And I did wax a bit pedantic about because I could use this material for talking with my team, but yeah, I wasn't quite sure what he was hung up on, and I did see some mistakes in the pseudocode, but sometimes when you have pseudocode, you can sort of simplify your way out of describing what's the problem. So hopefully he'll come on and we can get some more insight into exactly what's going on there.
I think New Zealand is about 12 hours off from us. Is that right?
18. He's 18 hours into tomorrow. 18 hours ahead.
So this is actually morning for him.
Well,
No.
it's 8 plus 6, so that's 2 in the afternoon there tomorrow.
Oh, so it's a reasonable time to hang out on a COVID day.
Yeah. I just sent him an email because they went through a time zone change not too long ago, and it confused, it got out of sorts on the calendar invite. So I sent him a note in case the timing was mixed up. But while we wait for that, because it sounds like that PID discussion could be a pretty good one, especially if we can get him online. Why don't we move on and move over to Doug? And I think, Doug, you had some stuff to show and tell.
Well, okay, let me see my picture here. Okay. I went out and asked Ray last week for suggestions on the one he got, but I also had the problem of not being, having a lot of patience. So while he was writing me the letter and telling me exactly what I should have got, I went ahead and got something else, which is, it costs a little more. It's got some additional features than the one Ray has, but whether they're useful on a robot, I doubt it. It has a real 12mm lens, which I think his just has a pinhole lens.
Right.
And it has a 500 milliamp hour lithium battery, so you can actually, I don't know if anybody can see this. I'll turn it on here so I can figure out where all the switches are.
Yeah, you have to hold it kind of still because
I don't know if you can see it, but it actually, you saw the screen change. And I have worked through, I went ahead and did their kind of like their video LED on program just to see that, the camera is working. And my first impressions are, though, somebody spent a lot of time putting it in this little case and everything, but they did things a little bit, a little wonky. So, I'm not saying that it's a bad computer, and I think the one Ray has, which I think is about $22. It's called the Max MAIX.
Pi.
No, it's not the Pi. It's called Lid or Q. Huh?
I think it's called the Dan dock. I don't know.
Yeah, the dock.
Yeah.
Yeah, and the dock is pretty good. So that there's, like I said, there's a few niceties to this. It does have, I don't think yours, the base model, the one of the dock doesn't have Wi-Fi. This one has Wi-Fi.
Right.
But again, you know, if you've got what you're doing is having a basically treating it as a sensor that's going to go on a robot. It's going to be powered by the robot. It's going to communicate with the robot. You don't need Wi-Fi for it. You don't need the battery. You can buy a 12 millimeter lens for a few bucks. So I still think the Max, what did we say it was? Max Dock.
Yeah.
If you buy it with the screen and it comes with the screen and the board, I think that's probably the best deal. So it looks like, yeah, Ray's got it in a 3D printed case. That's the other thing. He can actually swing on this one. They say you can mount the camera on the back, but they don't tell you. The thing is, they give you this little tiny lead, and if you put it in on the other side, it's equivalent to flipping a motor from the left to the right. The leads change, so you'd have to twist it, and I don't think it would survive it. So basically, you have the screen and the camera on the same side all the time.
Oh, okay.
Yeah. So anyway, next week, like I say, I should have by that. Like I said, I'm looking into some of the. They have several IDE options that you can do, and I'm trying to figure out which one I want to go with.
Mm-hmm.
But so the first thing I'm want to tackle. I did some reading, and I want to tackle. Plus we've also had. God, I can't think of his name right now. Who's the gentleman who had the eye injury last year? He's
Ron Grant.
Yeah, Ron Grant. Well, so Ron.
Oh, yeah.
So Ron is the approach that I plan to take is a little bit like his, where he had 3 lines. I think, Ray, you're doing something similar. 3 on the sensor, you're monitoring 3 camera lines, and then from that projecting where the line is really supposed to go.
Mm-hmm.
And so that's what I'm going to use it. The one I've been working with is a little different. Instead of a line, it basically is a band. So you have 3 bands. And so instead of looking at the differential of essentially of a single line, you're looking probably at the differential of the actually like a little rectangle. Mm-hmm. Otherwise, you got a band across the camera that you're monitoring. So the line should show up as a little rectangle somewhere on that band instead of just a line where you just have a single pixel. So anyway, that's what I'm looking at right now. I don't know how far I'll get, but hey, you got something to play with, Spent some money.
It's
So
a good time.
where I am.
You have on that, yeah.
Yeah.
I have an observation. I've noticed that for the times I've played with cameras and for others I've seen play with their cameras, that when we go out and buy a camera, we spend a lot of time choosing the best, fastest frame rate, highest resolution camera that we can get. And then when you actually use it, you lower it down to, a 32 by 32 array at a frame rate of 10 frames per second or something like that. The actual use of the camera is very, very low res, but for some reason, same thing with me, when I'm in the mode to buy the camera, I want to buy the highest res, fastest camera I can get, but that actually turns out to be not just overkill, but it's a pain in the ass to have that much bandwidth to have to deal with. And when you actually get through with all the data processing, you know, you've broken it down into, well, I'm just going to look at 4 scan lines on the screen, and I'm going to break those into 32 bins or something like that. It ends up at probably the lowest, cheapest, lowest resolution, and black and white. The cheapest, lowest resolution camera I could have gotten would have worked fine.
Yeah, I don't think this comes with a, I think if you were like looking at this as a, if you were looking at this as like a phone camera, this is like, you know, flip phone type. I mean, I don't think it's a very, you know, and
megapixels, I think.
if you're using the LCD, you're using, what is it, QVGA. So that's a quarter of a VGA screen. So that's like 320 by 120 or something.
240.
240, yeah. So I mean, these are really aimed at OpenCV and AI type applications, neural net. They're not. They're pretty. They've avoided what you're talking about, Dave. So I mean, I know on the Husky lens, which I showed last week or the week before, you know, they didn't quite do that. They had a 2 megapixel camera and which would be equivalent to, like I say, a 640 by 480, I believe. And they also had a 5 megapixel camera, which was better, but you know, you could buy the 2 megapixel camera. So you're right.
The first video application I ever did, I was just trying to emulate what I was doing with photo cells for photovore behavior. So basically, split the camera down the center, average all the pixels on the left, average all the pixels on the right, and then I ask the singular question, which side is brighter, and issue a turn toward that side, actually with a little dead zone in the middle. So there's no reason to really use a camera to do that, but I wanted to see if I could get the same kind of behaviors as a photovore behavior. But all my experience working with cameras is that I'm constantly reducing the resolution and reducing the frame rate to make it usable.
And even
I will say,
vision, you'll wind up like blurring it and adding noise anyhow. So
Yeah,
I
right.
think the best thing to get with a high quality camera is low light.
Yeah.
I do find that I will like up the price for a camera to get better exposure control and autofocus. You're right, most of the time that's not needed, but it sure helps when sort of testing vision algorithms at different resolutions and things like that. So with some of the more complicated object recognition stuff, it does come in handy to have the ability to pick up the object in different light levels very, very similarly.
Kareem, you guys have used a lot of open CV processing, is that right?
Yeah, OpenCV and TensorFlow and stuff like that. Euphoria.
So do those for the actual systems that you fielded, do you tend to find that you go to lower resolution images, or do those process full res images?
Well, they're almost never full res, and they'll often do a pyramid type of stepping algorithm. So you're looking at it from multiple resolutions, depending upon what it is that you're doing. So yeah, they don't normally require the kind of resolution that's available on a webcam, but when two different webcams offer a different range of light sensitivity settings, we'll go for the one that has the higher end capability.
So you'd like to be able to control things like the brightness and contrast and all that stuff, which you don't really get with the cheaper cameras.
Yeah, we have a lot of different kinds of environments that we operate in, especially at my house where we're operating in a tent over a pool and with really bad lighting in it. So and yet we're trying to test our algorithms in that situation, but it's best to be prepared for all sorts of different kinds of lighting environments when we go to compete.
Well, Carl, didn't you a couple of years ago you won some contest for recognizing objects and approaching them with a robot? And I think you guys Did you guys use a smartphone, or what was your camera for that application?
What was the camera? Okay, you're talking about the beer funding robot that Dave Ackley and I and Omar and the other guy went out to won a trip to Vegas for with AT&T's hackathon.
Yeah.
So for that beer funding robot, we used a Microsoft Windows phone, of course, just before that went obsolete because of our penchant for picking obsolete products. And that we used that phone to take a picture, and I think it was sent up at not quite full 5 megapixel resolution, but it was still sent up at least VGA, maybe higher. And we sent it over to IBM's Watson Visual Recognizer. So at that time, which was now already 4 years ago or more, we and none of us really knew what we were doing like we do now. At that time, we just used this available API, and we put the image up there after we trained it, and it told us what was there. Which you can still do, by the way. Google has it, IBM, Amazon Web Services, Microsoft Cognitive Services. There's tons of APIs that can do that in the cloud for you, but we have a kind of more embedded, localized approach, I think, in DPRG.
Yeah. Now, one thing I have noticed about cameras, that people are specifying is how far down the resolution can go. Like some of the sensors can't go to like a 32 by 32, Dave. They might only be able to go to 1280 by 1920. That might be the smallest they can do. So when you're buying one for this, you do have to make sure that the camera specifications say you can select real small resolutions. And
I guess I was referring to actually sampling at a higher resolution, but then the image processing itself, the software ends up, binning the whole thing, and you come down to the usable. The usable input to the algorithm is 16 by 16 grayscale or something like that for all the money that you spend on the camera. The software itself.
Yeah, I understand, but I'm just saying is if anybody's buying a camera now to use for this purpose, they need to make sure you can get down to those small resolutions, because you can buy a camera that can't get down anymore because they're made basically for phones.
Yeah.
I'm just saying you be careful about what camera you buy.
Unless you're prepared to feed it through some post processor like OpenCV that'll chop it down for you.
That was my comment.
So many options.
Yeah.
Is the camera that you have from CPED?
Yes.
Yeah.
Okay. And is it looks like it's programmable by Arduino. I mean, the Arduino program.
Okay. I'm not, Jack, they do have what they call a Maxduino or something, is it called Maxduino? I can't remember.
Yeah.
And I don't know, of the different flavors, I'm not sure which ones, what the difference is between them. I think the Maxduino might just simply, I know you can use the Arduino environment, but I don't know what keeps you from using the Arduino environment, say on this particular board.
Okay.
I don't know.
Mm-hmm.
This is meant to be MicroPython.
Okay.
But I think even the Arduino one, the Max Arduino, it comes with Mac. They're all using the same chip, and I think they all have the same firmware. So I don't know what the difference between the flavors are.
Okay.
But that's why I said I think Ray's got the right one, and I think it's called a dock.
Okay.
Docks. Dock.
DOCK.
Yeah. Mine's a Max Go.
Dan Dock?
Yeah, Dan Dock is,
Okay.
I think, the full name for it.
It looks like it's under the Maxduino website, though.
You can get it on you can get it on Amazon.
Oh, okay. But it's not a Max Duino?
No.
The one that I
Okay.
got is not. No, it's
Oh,
just
okay.
the Dan dock.
Mm-hmm.
And
If you think about it, you could put the link in the chat, and then we'll know what you got.
Yeah, I'm doing it,
Oh, okay.
I'm doing it right now. I'm doing it to what I think you should get.
Oh, okay. Thanks.
Not what I got. All right. I think this is it's cheaper, and I think it does what you want to do with your can I present for a little bit, and I'll just show it.
Yeah, present now, but bottom right corner.
Oh, okay, I got it. Come on. Okay, now let's see. All right, you should see. Okay, do you see this? This is here at Amazon Smile.
Not yet. Did you share a window or a screen, or?
I said show the whole screen. Should, okay. Let me try again. What are you seeing now? I see Carl.
I have set the jack at the moment, but.
Oh, wait a minute. Okay. Okay, I can't seem to hit the share button. Share button is grayed out.
Present now, share button is grayed out.
Yeah. Well, let me try again.
Okay.
Okay, I see the difference. Here it is. Okay, now it should be there.
Oh yeah, now you're presenting.
Okay.
There it is.
Yeah, so you can see it's $22.90, and it doesn't come with any case or anything, and you're going to have to put a case on it. But it doesn't have things. You're not buying things you're probably not going to use. Okay, and I'll put the comment in chat.
Nice.
Okay.
Cool. Thanks for the demo there, Doug. All right, so if we move next down the list, Mr. John K., do you have anything to show from last week, or you've been just sitting idle doing yard work?
A little yard work, main thing, well, and work, actually work. I'm doing work from home, which is interesting. I'm so used to my desk at that office. I'm not, yeah. But anyway, so hence you'll notice I've changed up a little things. Most other things I discovered, like issues and whatnot. So the thing I did notice last week that was interesting. I don't know if y'all have looked at that Boston Dynamics spot robot recently. We call Adam Savage, or how you pronounce that last name? SAVAG. He has a series of videos. So I would say, go watch those videos. It's impressive how that little thing works now.
Yep.
I was like,
they
wow.
have it hooked up like a dog sled, or in a dog sled team.
Yeah, one of his videos he has is where you use the little cart, like, the real horse racing where you have the guy being pulled type thing.
Yeah.
Yep, that was interesting. As I said, it was. I was surprised at how well it can move now.
I think if you have $10,000, you can have one of your own.
Well, I was saying 20,000. I thought was the number I heard, but I didn't really research it.
Yeah, I thought it was at least 10. I'm not really in the market for one, so.
Well, I was thinking we could build one a lot cheaper. At least I glanced at Thingiverse, and there's one or two out there. Well, it wouldn't pull the car, but
if you do Mythbusters episode for several years, you can buy whatever you want, right?
Yeah.
Like he did.
Carl,
but
Carl, I told you I didn't have anything, but I actually had forgotten. I set out a little board here I was going to show. Is this the time to jump in? Is this a good time?
Yeah, why not? We're just working our way down the list. And by the way, Murray, you came on board. So what we've already covered is this camera stuff, a lighter demo, and what we have yet to do is now Dave's demo. Mike has a claw machine demo. I think there's a bunch of guys ready to talk through PID loops with you.
Oh, cool.
And I'd like to show a progress demo on my SPI communication from Raspberry to Arduino.
Welcome. Sorry, I don't know why I was having trouble translating time zones. I've got it on my phone. We were having homemade udon noodles, handmade homemade udon.
Very nice.
Yeah, it was very good. So yeah, but thanks. Good to see all of you.
Yep. Welcome back. So Dave, I think you had some.
Well, I've actually showed this before at the club, but I thought I'd just do a repeat because last week we were talking about hooking up microcontrollers to robots and the rat's nest of wires that inevitably ensues. And so one of the things I've done, and Doug actually has a couple of these boards. This is a ST Micro Nucleo, which I think you guys are familiar with, which is what I've been running on my, am I holding it up? There we go. What I've been running on my current robots. And it has what they call ortho connectors here. And it's also then compatible with Arduino. It's got an Arduino breakout on it, so you can plug Arduino cards into it. And the pins, as you can see here, let me see if I can hold them up. You can see the pins actually extend through the board out the bottom, so you could plug that into another connector. And what I've found is that on my robots, typically, when you need to hook something up, you need to hook up a motor, you need to hook up an encoder or a sensor or an actuator or something like that. What you need in addition to the signal is you need power and ground. And this particular board, you've got like 2 power and ground pins. I'm backwards here. So basically that becomes really difficult when you need to hook up a whole bunch of things. And so what I've found is more useful, and I've had this on all my robots. This is a little breakout board. This is the one that I hand wired. These are the ones that I had, what's that, Oshkosh make for me. They actually make really nice boards. Ron Grant laid this out for me. Ron, are you here? Ron's not here. Thank you, Ron. But basically what it does is, see if I can hold this up here, is that you have a bus on either side, and that bus consists of ground, power, and 2 signal pins. Because in point of fact, you almost always need pins in pairs. So for example, for a UART, you need transmit and receive. For encoder, you need the A and B channels. For a motor driver, you probably need a left and right motor, and so forth. So they're all laid out so that every one of them, and I don't have a handy connector here, but each one of them then takes one of those standard little pin connectors, and this just plugs in. Am I holding it up here?
Yeah. Looks good.
Such like as unto that. And then all the connections are actually done here and here and not to the board itself. One of the things that allows you to do is, if you're like me and you maybe hook something up wrong and burn your board out, then it's real simple to pop this $10 board off and plug another one in without having to undo anything else. And anyway, I made about 15 of these, and James helped me do the surface mount parts, which is really just the bypass capacitors. And I have a bunch of them, so if anybody else wants one and is using, it fits this standard Nucleo pattern, I'll give them away. I'm not trying to make any money off these things. But the idea I'm trying to suggest here, and let me grab a convenient robot and I'll show you how those are actually hooked up. Hang on a second.
I like the idea that someone can just say, I'm going to go grab a convenient robot.
Not everybody can say that.
No.
Well, let's see here. I need to be able to see myself. There we go. This is the RCAT robot. You can see that same card is right here, and you can see all of the connections are on either side that go to all the sensors and the motors and everything else. And this particular processor is mounted up on standoffs so that all those cables can be wrapped in underneath the processor. So you don't end up with thousands of, oops, I just bent it, thousands of cables that make things hard to get to. So that's what I was actually trying to describe last week, only poorly. But I had a little show and tell this week. So that's all I have to say. Any questions?
No. Hey, Dave, I have one of those. I have one of those boards, but it's not populated. If you have one with capacitors on it already, I'd like to do that because that's such a pain for me. My eyes aren't good enough.
Hang on just a second. Yes, I have one here that already has the capacitors on it. And if you can see there and there. And James did those for me.
Yeah, that's great. I mean, I don't, like I said, I have the bare board, but no capacitors. So
well, the only other thing it requires is you have to put on the connectors here and here, and the ones that the sockets and the connectors. But that's tedious because there's so many. Ron also designed this nice custom wiring, and there's a 3-volt bus as well as a 3.3 as well as a 5-volt bus, which is kind of handy. So yes, I will get you one of these in some better world than this when we can actually physically approach each other.
Well, if you send it to me, do you have PayPal?
If you will just send me your address, email me your physical address, I will drop it in an envelope and mail it to you.
Okay, thank you, Dave. I'll email you that. Not in chat.
Nice demo. Thanks, Dave. We'll send Howard. Harold was asking last week, so we'll have to tell him to peek in around 8:10 on this to see what you're doing.
Yeah. The other thing too, Dave, that you didn't mention is that if you wanted to, you can use any of those boards that have the same configuration. You know, there's a line from anywhere from a Cortex M0 to a Cortex M7 now. So you could upgrade it or downgrade it as you wanted to without changing the wiring and everything. Though I think you used a 405.
Yeah, that's an M4.
Yeah.
Cool. All right. So Kareem, you're next in line. Any managed to do any fun stuff this week, or just chores?
Mostly chores, but I wanted to follow David's lead and grab a very inconvenient robot. You guys have seen this before if you were at the team's presentation to DPRG. So I wasn't planning to, or that's actually version 2 of the robot. So they were in the progress of completely rebuilding it from scratch. There's actually another one in that robot tent right now. That's the one that they're currently working on, or had been working on. And this one is not quite, it's like that far from being actually operable. But, you know, they haven't been coming over since the shutdown, so.
Kareem, is
this working on work.
Yeah, Kareem, is this your second robot that, you know, you said you like to go to competitions with 2 robots? Or is this
is the one that they would have gone to Worlds with. And it does have a number of improvements over the previous one, including the fact that, like, the first time they sort of designed the base plate and then the turret plates, they designed them, but they just printed them out on paper and then use that as a template to cut out with, cut out the polycarb with, what do you call that? Not hacksaw or a jigsaw. But since then they've gone to full CNC, and so the newest one is, you know, many fewer mistakes, and it looks nice and clean and pretty, and it should have some real improvements in its operations as well, and reliability. So it's a nice robot. It's too bad they didn't get a chance to show it off. I thought they were actually really in the running for a significant major award at Worlds this year.
No,
Well,
bad break.
Yeah, well, it happened to all of us. But hopefully I'll get them to resume work on it over the summer, and maybe we can have a final presentation to DPRG and show you what it was really capable of.
Yeah.
It wasn't
Yeah,
quite
that'd be
there
nice.
when we were doing the regular demo, that first demo to you guys.
It might be nice to see the two next to each other and see how you improved it.
Yeah, they had a plan to do a reveal video that would have shown both robots running at the same time.
Okay, cool.
So maybe we'll get that done.
okay, cool. Thanks.
Mhm.
All right. So just a time check. We have about 35 minutes left on the reservation. We can go longer if we like, but we have 3 things left by my count. We've got the claw machine with Mike, PID loop discussion, and then my little 5-minute thing, whatever that is. Mike, do you want to go next on the claw machine? And you're muted. And
Oh,
video's muted. Mike has left the building. Okay. Well, why don't we jump ahead then and talk PID loops? So, at risk of a discussion
Mike's
that
back.
could be a very long time,
Mike's
I know
back.
there's all kinds of emails going back and forth on the D list today. So maybe Murray, from your own spoken words, we can see your face. You want to just give a brief kind of summary of the question and kind of where you are after all these emails bouncing around?
yeah. I had just sent a fairly long reply to Kareem just before I went off to lunch, and so he probably hasn't even had a chance to read that. But
I haven't seen
I'll
it yet.
try to recap where I'm at. I had, my robot was just running as a straight motor controller, just to send power to the robot, and it had no feedback or anything originally. And then I got the motor encoders working so I could get velocity, but I hadn't figured out how to get that into the loop at all. And so I was looking around for any Python-based PID controllers and didn't really find any. There may be some out there, but I did find this one. I think on the list someone had mentioned Brett Beauregard's PID controller for Arduino. And so over the weekend, I was trying to port it to Python for Raspberry Pi and for my motor controller. It's got like every feature under the sun, and it's quite complicated, and I failed in porting it. And so I think Saturday night I gave up and from scratch just wrote a PID controller based on the algorithm that I could find, which was on another website. And I actually got it running. I mean, if I have the robot sitting on my bench so the wheels can rotate, and I could grab the wheels and I could actually see the thing compensate, and I tweaked the PID values and managed to get it kind of working. I agree with Kareem that the I value is the most complicated. The question that I asked the group to sum up was that I'm currently getting a value from the motor controller on its power, which is whatever that is, probably PWM or whatever, but it's getting a 0 to 1 value on power, and I'm doing some calculations and then setting power. So that's my loop, but it's not velocity, it's power. And so my best guesstimate on that was to say, okay, I'll do a rough translation of velocity, which I'm going from 0 to 100%. I just did a rough calculation of velocity off the encoders to power, and then setting it based on that. So I stopped taking a reading off of the motor power and was now sending in a hacked version of the velocity, and managed to kind of get it to go with that. But it never actually matched the target velocity because, of course, it wasn't getting an input from the motors. I guess what I was getting at was that the relationship between velocity and the motor input and the motor output is tenuous. It's just this hack that I did. It was just a number conversion. And so I couldn't get it to actually, I can't say set velocity to the motor. I can only say set power. And so what I ended up trying to do, and which I've kind of almost got going, is to make a power-based PID controller, wrap that in a velocity-based PID controller, where I basically set I take input of velocity and then basically send in a value into the power controller as another term. So I've got P, I, D, and V, and try to adjust the power controller based on what the velocity sees. That's still, I don't think I've solved the problem, and that's kind of why I sent the message into the group. That's
yeah,
kind of
Murray, I think you're making it more complicated. So let me put it this way: your reference is a value, and it should be something. It is now. It's nice to convert these into velocities and talk velocities, okay? But on the very beginning, the very basic, you can talk. You can encoder ticks per period. Okay, so every time it loops around, it counts and gives you the incremental encoder ticks. As you get more sophisticated, you're going to want to talk velocity, and you'll take encoder ticks and take the diameter of your wheel and whatnot, and you'll end up in creating a velocity. But at first, just think of it as the input is going to be, or the feedback value is going to be the number of encoder ticks per period.
right.
Your reference is the number of encoder ticks that you want. Okay? So you might say, I want 10 encoder ticks every time this thing goes around. Or more likely, you might want to be saying something like, I want 147 encoder ticks, or whatever it is, depending on your encoder. Because if your encoder is on the end of the motor, you get a lot of encoder ticks per period. If it's on the motor shaft, on the gearbox shaft, you get relatively few. That's not a good place for you to have an encoder. You really want the encoder on the motor shaft.
To be clear, Doug, to be clear, I'm using Hall effect encoders on the motor shafts, and I've measured over quite a lot of measurement. I'm getting 494 ticks per rotation of the wheel, which is a pretty good number, actually. And and I've even gone to the trouble of trying to figure out what the diameter of the wheel is, and I have an idea of how to set actual like meters per second velocity, but I am not trying to do that. I'm only trying to say, I want to have so many relative ticks per second in terms of. I agree with you.
Okay, so I'm saying on the first level, so your reference value is going to be ticks per loop.
Right.
The number of ticks per loop that you get, Doug, will come out.
Murray, what is your loop? What is your loop rate? That is, you read an input and you generate an output, and then you do that again. What is that rate?
I took that from you, 20 milliseconds.
So you're doing that at 50 hertz?
Right.
Okay, and so it's not really the number of encoder ticks per wheel resolution that you're interested in. What you need to know is when you run the motor at full speed, how many ticks per 20 milliseconds do you get? Do you have that number?
No, I don't, but that's a good point.
So that would be full speed. That's what you would scale to 100. That's the way I do it on mine.
Okay, thanks. That's actually what I was looking for, I think.
That's actually good.
Yeah,
I was trying to keep it down at a lower level. But
simpler way, even depending on what resolution of math variable you want to use. What I'm hearing is that is the fundamental concept of control loops, where you've got a set point, so you want the motors to go at so many ticks per period, and then you've got an output which is going to basically be power or voltage or whatever the motor needs to turn at different speeds.
No. You're falling into a trap.
No.
The output is going to be the number of ticks that you get per period.
No, that's the error.
No. The error is the difference.
Well,
Well,
where I was having the
Good
problem,
web
of course, that I can't actually set the motor to a certain number of ticks. I can only set power, which I guess is 0 to 100% or 0 to 1.
Well, that's the beauty of PID, is that if you feed it in, I want 10 ticks per loop, and you're reading your encoders and you're getting 7, the encoder will turn the speed up. I mean, the PID loop turn the speed up.
Yeah,
that's exactly right, Murray. You don't need to know what you're telling the motor. It's actually arbitrary. What you need to know is the requested number of ticks per 50th of a second, per 20 milliseconds. Is the requested number higher or lower than the number I read back from the encoders? And if it's lower, I need to increase the voltage, power, whatever you want to call it. And if it's higher, I need to decrease that. And if you do that just with a proportional controller, that'll work pretty well. That is, all I do is I say, I'm wanting to run, I would like to get 100 ticks back per unit. And what I'm measuring is 50 ticks back per unit, so I need to turn up the value. While I'm getting 150 ticks back per unit, I need to turn down the volume. I don't really care what the value is. The PID controller does that part. The problem with a pure proportional controller is that it tends to oscillate around the set point. That is, you'll overshoot. And you try to say, well, I'll turn down the proportional constant. And all that does is really make it arrive slower. It doesn't keep it from overshooting. So that's what your derivative value does. Your derivative value allows you to turn down the proportional value, and the derivative says when the difference between what I want and what I'm reading is large, then the derivative is large, and so it'll kick you up closer to the set point. When the difference is small, the derivative is small, so the proportional takes over, and you can zero in on the set point. Now, I offer the caveat that I do this differently than the way it's been described on the list. I use a PD controller which feeds the integral value. The integral value is the output of my PID controller. So I think about it like as if it's the position of your accelerator pedal. And so if the difference between what you want and what you've got is 0, then that just means you're not changing the integral value. It's not going higher or lower. If the difference is not 0, then obviously you're moving that value up and down. So the I value I use directly drives and the motor, and therefore you don't have the wind-up value. The wind-up problem that Kareem was talking about has to do with the fact that basically the integral can build up endlessly. So you end up with a huge integral, and you have to have some way to discharge that or pull it back down. This avoids that because basically when the robot is doing the speed that I requested, the error is 0. And so the integral, which is the output of mine, doesn't change. When you sum whatever the current value is with 0, it stays the same. As I say, I do this a little differently than the standard.
Well, I think the eureka moment came a few minutes ago in this conversation when it was, and I knew that it couldn't be as complicated as this because having a wrapped velocity PID around a power PID sounded way too complicated. And you're right. All I needed to do was get the velocity being ticks per second. So all I need to do is, as you said, set the motor at 100% or whatever I want 100% is, get a measurement of the number of ticks per second, and then do the calculation necessary to say that's 100, and then that's really all it is, isn't it? It's not much more complicated than that.
But that is a little bit of a trap. I mean, I think David gave you that answer, and it helped you get a sense of scale for what the numbers actually mean in terms of voltage. But again, if you go back to the fact that you don't really need to know that, the PID will take care of all of that for you. It just knows that it needs to increase. The only thing that you'll notice is that once you get up to 100% voltage, you can't go beyond that, so you can't oscillate beyond that either. But you will naturally find out what your maximum voltage is, or PID setting, because it's just going to sort of saturate there.
And
I know you don't really need to know. You don't need to understand you don't have to have a formula in your head for what the encoder ticks per meter or per second are in order to control that output voltage.
I remember when I was writing the controller that I think it's the I value is the sum of all the errors. So if you let that run for hours, that number would get very, very large. And is that what you're talking about?
Yeah, that's why you need wind-up control, and it can happen very, very quickly, actually, right? As, you know, and it'll get worse if you have a very short loop time. You know, the more readings you have. So there are lots of different techniques for unwinding that built-up error. Because if you think about it, for most circumstances, or at least the way we use it, the I value is meant for that regime where you're trying to get precisely at that final set point, because proportional is no longer working, right? The error is too small for proportional, so it's not actually helping you move the robot. There's no approach. There's not necessarily a lot of approach happening either. So the derivative isn't helping out. So the integral is your way of telling that. Of the robot's understanding that it's just a little bit off of where exactly you want it to be, and that's the only regime in which you want it operating. If you're like way off and you're doing proportional control from say 90 degrees away, if you're trying to rotate say a turret back to 0, you don't want to be building any error in the integral calculation for that, because it's just crazy large. And then you just have to unwind it, and that'll actually cause more oscillation because then you got to overcorrect to undo it if you don't have wind-up control. So there's a lot of different things like zero crossing, resets, and things like that. There's different ways to do wind-up control.
Well, you mentioned that in the video, the YouTube video from David, that he mentioned this idea of a leaky interval, and I have to go back and look at that. But I think maybe exploring
that's a different concept.
Oh, is it?
That's a different. It's nothing to do with PID.
Okay, all right.
What it is a way to, Dave, you kind of might want to be better on this, but it's kind of a way to control a time. So let me give you an example of a leaky. The idea is you have something that every time it goes through the loop and you have an error, you add 1. Okay. And you keep adding 1 to it. But if you don't need it, you don't add 1, you take 1 away. All right? So it kind of is like a bucket with a hole in it. And so you try to keep, if you don't need it anymore, it'll eventually go back to 0. All right? I'm not saying this very well. It's a very important. It's a very important concept because you will use it in your code a lot of places. Go ahead.
It's basically for controlling time. It's a way to control time, and the analogy that Doug used is a very good one. If you imagine you have a bucket that's got a hole in the bottom, and you're pouring water in the top. So if you pour water in the top at a rate that's equal to or less than the water flowing out the bottom, then the bucket basically remains empty. But if you start pouring water in the top faster than it can leak out the bottom, the bucket will slowly fill up. And you have some trigger point that says if the bucket gets above a certain level, then do something. And I use those a whole lot in control systems. And a simple one was, and probably the one that was in that video, was talking about keeping track of bumper presses. So this leaky integrator basically is a number, and you put a value in there. Every time you get a bumper press, you accumulate a value, and then each time around the loop, you subtract 1 from that. So let's say every time I get a bumper press, I put a 10. I add a 10 to that value. So the first bumper press puts in 10, and the second one it'll be 20, and the third one it'll be 30. But each time around the loop, it's subtracting 1. So if those are coming at a very slow rate, then those will decay away from 0 pretty quickly. But as they come in faster and faster, they stop leaking away and they start to accumulate. So you can know that I'm getting a whole bunch of bumper presses in a very short time. There's other ways, for example, in the sonar, to measure what kind of noisy environment is, you use a leaky integrator. But that's separate and distinct from the thing Kareem was talking about, which is a way to get an integral to unwind. Carl, can I present here? I've got a piece of code I could show.
Great.
How do I do that?
The same lower right part of your screen where you hit the three dots to have it call you. There should be a present now.
Present now. Okay. What happens if I press that?
Click it. And then pick your screen. It's the easiest, or application window. And then
If you're using Google, make sure you use the Google tab. What you're going to show is on Google.
so
Did that
yeah,
do,
there you go. It's coming up.
did that do anything?
Yep, we got it.
Okay, there's a piece of code here. It should be called motor command. And this is where the PID control is called. And so if you jump down, let's see, can you see my cursor?
Yep.
Yep.
Okay, the way I control my robot, I don't control a left and right motor. I control a speed and a rotation. And the left wheel is the speed plus that rotation, and the right wheel is the speed minus that rotation. You can think of those as speed and steering. So here I've got two variables called left and right wheel, and I've handed in the values speed and rotate, bot speed and bot rotate. So I'm calculating that left and right wheel. And then there's a clip to be sure that we're not over the maximum value. And then this is a little complex, but basically I have an integer PID and I have a floating point PID, and I've actually been playing around to see if one works better than the other. And I thought maybe the floating point PID would work better than the integer PID, but it turns out that it doesn't. So just ignore that second one. So here, basically, it says left wheel is equal to the PID for the left wheel and the PID for the right wheel. I'll scroll on down here, and you can see that there's a PID left and a PID right. Basically, what it says is the right proportional error is equal to the speed, which I am requesting, minus the velocity, which is the reading from the encoder. And there's a scalar there because I convert all these to 0 to 100. I normalize them. So I'm using a PWM controller where I have a pulse width of 0 to a pulse width of 100. And I scale the encoder values as described earlier, so that whatever my max speed is, I scale that to 100. So that's what that velocity scalar is doing. And then I calculate the derivative and the proportional, and that's what this here is the actual PID controller. This thing right here, where they're all summed together, and you can see that there's a plus equal there. So that's why I say my output is actually an integral. And if everything to the right of that plus equal is 0, it just leaves the integral where it is. That means the speed that I go at is the speed that I requested, neither higher nor lower. If it's higher or lower than the proportional, and the derivative will sum together to either increase or decrease that value. So in this case, there is no windup. When the robot's going the speed I requested, suppose I requested 50%, whatever full speed is, and I measured, and it is 50%. Well, then the proportional error will be 0, the derivative will be 0, and that right PWM value will stay whatever it was. It means that the output, which I say in my case, the output is the integral, and the output is at the proper value. So this does not have that problem where it creeps up but does not actually make it to the set point. This actually fits the set point, but the derivative there keeps it from overflowing. Am I talking too fast here?
Yeah, well, I think you are missing slightly. Okay, and when you have wind up is really when you get a value that is so fast that that is way above the number that your motor can go. And so what happens is, even though you may be correcting that you've got this long period of time when you're way over it, so you overshoot, and that causes you to oscillate when you have wind up. So I'm not sure.
I see what you're saying.
I think there's two different issues.
That's actually handled by the line I have highlighted there. You see it called the function called clip.
Yeah, well, that's one of the ways of managing. Otherwise, one of the ways of managing a windup is you set a max value that you can have, and it'll never go above that. See, so you essentially have in here, Dave, a wind-up control line. That one that's highlighted. All
Yes,
right. That is. It's not that you wouldn't wind up. It's just that you're clipping it once you reach a point, and that's what's going on there. It's not that with that plus equals you would wind up.
That's correct. And an example of when that would happen is, suppose that you're in a real high torque situation, like for example the wheels are stuck, and you've now cranked the PWM value up to as high as it can go, and even so you can't get the wheel velocity up to 100% because the wheels themselves are jammed or something like that.
Yeah.
So it'll continue to kick that each time around, but this clip, you're exactly right, takes care of that. And you can see that the last step here, once you've determined those values, is I actually call a function that sends the pulse width modulation value, which, as I said, in this case is a number that's minus 100 to plus 100, depending on whether it's forward or backwards, which basically just represents pulse width, and it sends that to the actual heart there.
Yeah.
That's the last.
Okay, so just remember.
Help me out, David. I don't see where you're doing integral.
The integral is the actual output. Okay, so scroll back down here. Okay, here we calculate the proportional error. All right, which is the requested, which is called speed, minus the measured, which is velocity over the scalar, which scales it to 100. And here we're calculating the derivative, which is the proportional error minus the last proportional error, which we then save. And then here, the output plus equal. That's the integral. The output is the integral. So as I say, you can imagine that the output is, in point of fact, like the position of an accelerator pedal. And if we're going too slow, we're going to increase that value. If we're going too fast, we're going to decrease that value. So that's the integral.
That's the correction, but it's not the integral.
It's an integration. Plus equal is an integration.
I think this might just be a matter of terminology, isn't it?
Well, I would just call this a straight up PD controller because you're always adjusting something. Unless there's something I'm missing. It just looks like a PD controller to me.
Not unless you zero out right and left PWM. So yeah, it is an integration.
That's an integration because that's the same value from last time around. Right? So we have added.
Minus the clip. It's not exactly the same as the last before because it has the clip on there, but.
Yes, that's true. But normally the clip doesn't do anything.
Yeah.
In the normal case, and I generally run my robots at about 70% full speed, so I have a little overhead.
Yeah.
I think I may have inadvertently implemented what I'm looking at on the screen there because I basically I did the P, the I, and the D calculations, and I add them together, and I actually have an output value that is a plus equal of those, so it looks the same there. Now, for what you're calling clip, I think in your video you mentioned that you had a slew method or function, and so what I'm calling a slew is that if I try to send a value too high to the motors, I don't want the motors to go from 0 to 100 and break the gears. So I basically put a max on what can be changed on each rotation, and that's my slew rate controller. And so what I've got right now is basically rather than clip, if I send a number to the motor that's much larger than it has now, it automatically limits it at a rate that is based on the robot accelerating or decelerating. But then once I get near the main value, I set that slew value much smaller so that it actually tightens up the slew.
Yeah, but
so that happens at a level above this.
Yeah, okay. And you do need to have both. You need a clip and you need the slew.
I did
The
find it
rate-
interesting you put the slewing inside the PID calculation.
Yeah.
When I think we normally see it outside, or at least that's the way I've encountered it.
That's the way I do it. That's the way the slew, it's a rate limit that basically just says how much can I change when I call this function, how much can I change it? But that happens at a level up. That allows different behaviors to slew at different rates.
Okay. Yeah, I understand.
Okay, how do I stop presenting?
Go down to the bottom and stop presenting.
Down to the bottom.
Hey, Carl.
Yeah.
This is Mike. Can I do my demo before I lock up again?
Yeah, I think we need to move on, and especially in sense of time as well. So, Mike, you're up. Claw machine.
Okay. Do I present, or y'all see me, or what? How does this work? You want it big or small?
Your screen, you can present, or if you just want to use your camera like we see you now, then
I just want to. Okay, so here's the deal: is what I use for all that PID controlling. I just use rubber bands in mine up there. That's how I keep them together. Anyway, it's supposed to be a joke. Anyway, I do use rubber bands to help up here if you can see them. But anyway, okay, so I designed this thing. My claw machine is designed to take the little carnivals, as I explained last week, and I made it where I can disassemble this thing real fast. All these things come apart, and hopefully I put them in a box. Put them in a box, and I put this together within 30 minutes to an hour before the event. I made it actually for my church, Halloween carnival we have every year. And you don't add money. I still got a little ways to go. I got to make a case for but it's functional. I want to demonstrate it. And of course, the code is nowhere near as complicated as what you guys are doing. But I'm using an Arduino Mega. The reason why I'm doing that so I can add lights and sound to it later, so I have more pins. I'm using four stepper motors, and these stepper motors are taking the same. The Y stepper motors are taking the same information from the Arduino. I'm just splitting the signal to two different drives. I'm using these drives right here. Y'all have probably seen these 100 times. Can you see that?
Yeah.
The two dark. Yeah, y'all probably seen these. You get 5 of them for $11 or whatever. So I'm using those to drive the steppers. So anyway, here we go. We go right and left and back, forward, X and Y, and then I push the button and it goes autonomous after that. It runs a loop. And the kids, no matter what they do, they can't interrupt that loop. Okay, pick that guy up there. That's pretty heavy little deal there, too.
Any good
I think that would be
prizes in there
considered
yet?
a ballistic behavior.
A what?
And then back. Of course, we're going to put candy in there and stuff. And these are little presents my wife got at garage sales or something. Little, McDonald's stuff, So anyway, there's my demo, and I'm real proud of it. And I've been off and on this thing for about 2 years. I've done a lot of 3D prints threw in the trash that didn't cut the mustard. And so I've done a lot of different designing, and so it's ready to go. I got some wire management in the back. Thank you. So anyway, thank you very much.
Nicely done.
Elvis.
Maybe I'll put some PID control on it next week or something. I don't know.
Another rubber band.
There you go.
All right, that's it.
Way to go.
Very, very sweet. Yeah.
Yeah, elastic is like an integral. Stretch it out more.
Cool. Okay. All right. So then, if we swing around, shall I show what I've done in the last week?
Sure.
Sure.
Okay. Let me bring this up. Present now. Entire screen. This one. Go. Okay. So you should see Yosemite right now. All right.
Yep.
So what I've got, what I've been working on is over here. You'll see my club car donkey bot. It's a 2016 club robot down below with the donkey car cart stuff on top and a camera hiding in there behind all the probes. And the progress I made last week was that, as I mentioned before, I'm not using the servo signals to get from the Pi to the base like the normal donkey car. Instead, I have a SPI connection, right? Serial peripheral interface. And so I wrote my own library so that I can now use the PS2 controller, which talks to the dongle on the Mega, to drive it there locally, so that I have good control over the wheel speed, nice and responsive. But then now I have to get those values, my command values, up to the Pi so it can learn, and then I need to get the way to get the commands in self-driving mode from the Pi back down to the Mega. So what's going on here, and what you see on the oscilloscope, is on the bottom trace is my roughly 60 hertz loop. So every 15 point whatever milliseconds I go through and compute. And on the top part, if we synchronize on that, I have some loop back code running right now on the Pi. So what happens is that the Pi is going through, and it's basically every however many milliseconds, it's sending out values down. It's reading the values from the Mega, and it's sending values. It's looping the same values back down to the Mega. So the cool part is that if I stop this, you'll see that I mean, it's quite asynchronous, right? These things might overlap. Maybe they won't overlap. So, so that was a real interesting challenge, because all the libraries for SPI that I've seen on Mega want the Mega to be the master, and similar for the Pi. So what I actually have here is a library that I wrote, lets the Mega be the slave. So I have the whole kind of, I don't know if you call it semaphores or double buffering or whatever, but I have it so that even when these things collide in time, because they're asynchronous, even when they collide in time, they don't corrupt the values at all. They might delay it by one of these lower loops, but anyhow, this is cool because I got it working first in C on both sides, then on the top side in the Pi, I ported it to Python, and now that it's running as a loop back consistently, now I can finally go and integrate that Python into the donkey car code, and finally I'll be able to catch up with everyone else in the club who's been able to train their donkey car.
Nice.
So this is SPI, right?
Yes.
Okay.
Yeah.
That's cool.
Yep.
So what is this cool oscilloscope you have?
That's my USB oscilloscope right there. It's the older version of the one the club got jacked, or some of the guys got jacked. So it's just a handy little cheapy thing.
And it has BNC connectors on one side and then like a video connector on the other?
USB.
No, it's all USB. So actually,
USB.
Yeah, it's actually my my laptop here, so I can the window of my laptop, right? So.
Oh, cool.
Yeah, I wish.
Cool.
I wish that you see I was jumping around so much when I trigger on the top trace. I wish it had bandwidth limit on the trigger, but it doesn't. But I mean, for what it is, it's pretty reasonable.
Hey, Carl.
But
would you be willing to?
Handier than mine.
I look just like mine. That looks exactly like mine.
Yeah.
Several of us.
Would you be willing to put that code up in GitHub or so that we can?
Oh, yeah. It's actually there.
A tutorial on the website.
Yeah, the code is actually in GitHub right now, but the well, here, this is how I was going to show this, but it's not as documented as cleanly documented as I want it to be. But I'll put a link here as soon as I'm done showing you one other thing. So, like here is the or two other things. So here, as you can see my screen, where'd it go? This one. Where'd it go? I got too many windows open, too many screens. Just give me a moment here. It helps if you grab the right screen, and I will do that right here. So if we open a VNC to the Raspberry Pi, okay, so now you can see, so here is the Raspberry Python code, Raspberry Pi. If I stop that, you'll notice that the upper trace stopped because now the Raspberry Pi is no longer, it's the master, so it's no longer sending commands, but the Arduino is still chugging along at its own happy little rate. So if I restart the Python down here, you can see that starts up again. Or I can come over here and I can slow it down. And this is where I think, you know, some of the, you know, a lot of people had trouble driving driving in a coherent way with the donkey car. I think a lot of that just had to do with simply the sample rate on the Pi, because if I slow it down like this, now you can see that it's a much, the Raspberry Pi is coming at a much slower rate now. How slow is it? So look at that, much slower rate, right? And I found that whenever I had this in the loop, it was really hard to steer and control the robot because there's so much lag at it.
Yeah.
So that's how my design approach was to keep the faster, because this is more like the real operation. Like your donkey car is just like 10 hertz, right? So so the idea was that I would drive it with the commands to the Mega directly, and then the Raspberry Pi would just monitor. So whenever it's sampled, but it would always capture the correct throttle for the image it just sampled. That was my approach then to doing it this way, and well, we'll see how it works out in the next week or two, hopefully.
Okay, cool. But what I'm saying is, this looks like something that would really be nice as a tutorial on the web if we could do it.
Oh yeah, no, it's been very much in my mind, but I wanted to actually make it work first.
There is that.
That's been my bugaboo, right?
Yeah, it's a good idea. Carl, it's a good idea.
Yeah. So there you go. So I'll put the GitHub in here in the chat window shortly.
Okay, great.
If I can find the window, there's the control. And then Ray, were you doing anything this week? I think you're the last one on the list that we haven't talked
I
yet.
am, yeah. Yeah, there was it seemed like there was some interest in flow control for video stuff, and
yes, optical flow.
Yes, optical flow. Let me see if I can present. Anyway, the OpenMV has like, let me see, how many different examples of optical flow? Yeah, I should probably go to present mode. Hold on a second. And then present now. Entire screen.
You might, hey, Ray?
Yeah.
If you're gonna, okay, it looks like you're presenting, okay.
Yeah. Anyway, so can you see that window? It looks like, here, I'll blow it up. Looks like an IDE, maybe?
Mm-hmm.
Okay, so you can see that. Okay, yeah. So under examples, optical flow, I don't know if that's text is too small. Can you read it?
Yep. Read it. No problem.
Okay. 1, 2, 3, 4, 5, 6, 7, 8 different examples. Either like absolute rotation and scale, they're saying zooming, or just absolute translation, you know, moving it left to right or up and down. Differential rotation and translation, and then different different combinations with patches. So you can select like part of the image, and I'm actually let's see. This one was absolute rotation and scale. So I've got my laptop hooked up to the OpenMV H7. So if I do this, okay. So let's see. This one is rotation. So if I rotate the image, yeah, you can't do it too fast. I found. No, that's just the frame rate. Yep. Okay. There we go. So if I rotate it, figures we're in demo mode. It's not cooperating. It'll indicate that by that first number will change. That's for rotation, and then scale is in and out. So if I zoom back, okay, it's supposed to go negative. Yeah, man. Anyway, I'm kind of doing this by hand, and if you move too quickly, it doesn't keep up with it. But there's, several different examples of that. It seemed like several people were interested in it, and so I think you could probably. Oh, go ahead.
What's the bottleneck on your speed? Is it the processor or the camera? Why you can't move very fast?
Oh, it's doing a bunch of FFTs, like 64 both directions, and it actually takes a snapshot and compares. It does the FFTs on the snapshot and on the current video snapshots. It's like it pulls a frame out and takes a look at it. So it's doing a bunch of FFTs on the image. I think this one is, it's 64 by 64. So it's actually doing 64 FFTs vertically, 64 horizontally over both images. So if you move it too quick, it just.
Is that the processor not keeping up with it, trying to crunch the code?
I guess the question I have to ask, it says you're doing 74 frames per second.
Yeah.
Is that really half because you're comparing the two frames?
No, that's just a frame rate camera. This actually has the global shutter camera sensor on it.
Okay, so this really is an OpenMV.
Yeah, it's an OpenMV H7.
Okay, H7?
H7, yeah, with the global shutter camera it's a very sensitive camera, so it doesn't take a lot of light to get, super fast frame rates. So it'll do like up to 240, I think, in bright lighting, bright light.
Mm-hmm.
So, but it's typically 2 to 3 times faster than the OV series cameras.
Well, I mean, if you're actually making the comparison every 74, you should be able to move it pretty quick.
I think the camera can take snapshots very quickly, but it still takes a fair amount of time to do that processing.
Yeah, but the problem is then you have to be skipping frames.
Right.
Or you have to be lagging frames.
Right. So that's, if you move too much, it can't find, the correlation between successive processing of the, comparing the two, the original image that took a snapshot of and the snapshot that it pulled out of the, out of the video sequence, or a frame that it pulled out and treated it as a snapshot.
I guess the question I had, Ray, was, is it really using the 74? I mean, would this be a case where if you slowed the frame rate down, it might actually be more effective?
Yeah, I would say if you could speed up the processing to keep up with the frame rate.
Or match them basically.
Say that again.
Otherwise, if your processing can't keep up with 74 frames per second, then maybe you should cut the frames per second down.
Yeah, I think it's not an issue to me of keeping up with the 74 frames per second. It's more that it takes a fair amount of time to process. So even though the camera can deliver snapshots very quickly, it still takes a certain amount of time based on a 64 by 64 image to process it. So yeah, having, if you could speed up the processing part or reduce the amount of time that it takes to do it, then it could probably, the 74 frames would probably be useful.
Yeah, I guess the question is the software smart enough that it's actually sampling whatever's going? Otherwise, let's say you can only process at 30 frames per second. Okay, so is it actually smart enough to know to pick the every third frame, or is it trying to pick the next frame that's in the buffer?
Yeah, it's typically it's picking the next frame that comes up. So
okay, so
yeah,
like you want to reduce your frame rate.
It's still not going to matter because it still takes a fair amount of time to do.
Yeah, but what I'm trying to say is
all those effects.
You're always lagging otherwise if it's taking the next frame rate, and you would always be lagging by, let's say you can only do 20, that'd be every 6 frames roughly. You're always, now if you're doing it sequentially, you're picking a frame that's 6 whatever's in the past, so you're always way behind what's really going on. Am I making sense? Otherwise, if you reduce your sampling for the number of frames, it seems like you might actually be able to track faster, because that's all you can process anyway.
Yeah. Well, then your frames are further apart because they're slower. So your frame rate.
Yeah, but they're not in the past. They're closer to the real time.
Yeah, I disagree. I think if your frame rate is fast, your the time between frames is going to be much smaller.
No, think of it this way. Okay, time 0. Yes. Okay, let's say I can only process every 6th frame.
Yeah.
So frame 0, I process the thing. So the next one I process is frame 1, but my time is now at 6. So now I process frame 2, my time is really at 12. If I process frame 3, I'm really at time 18. And it just gets worse and worse and worse and worse.
Yeah,
but you're lagging in the past. It would be better to do at 0, 0, and then 6 and 6. I mean, the 6th frame, 0, then the 6th frame, and then the 12th frame, and then the 18th frame. Even though,
But Doug, is that really the way it's working?
That's what I asked him, and he said it's picking the next frame.
But
you can admit you might be running 6 through the. It also depends on how big the buffer is.
I think he meant the most recent frame.
Yeah, it's whatever frame comes up next. In other words, when it's finished processing, it grabs onto whatever frame.
Okay, that's the way it should do. Okay, that's cool. Yeah. Then it makes no difference.
Yeah. Anyway, what I meant was if you move the camera too quickly for a fixed processing rate, there's a lot of change between your frames. So, or if you're pulling it by hand and moving all around.
Yeah, essentially the area of interest moves completely off the screen.
It could.
Off the frame.
Right. Yeah. Anyway, so Carl, if you're interested in that, you might want to look at that. Cool. The other thing that I've been doing is working on the lawn mowing robot and trying to do triangulation and trying to figure out what the best orientation would be for the camera to work with tangents and pixel orientation in the screen and trying to get angles out of it. Anyway, I was able to basically get what looks like pretty good position accuracy out of it. What I was doing, I'm gonna get rid of this one thing here. Hold on. Fix it. Leave that one. Hold on a second. Gotta change setup. Okay, got plugged back in.
I think I found the noise source.
What? Me?
Nothing happened.
Nothing. Okay, hold on a second. Details.
Nick, the nights that say Nick.
Caption. And your entire screen. Share.
Hey Ray,
Yep.
you said triangulation, but did you really mean trilateration?
Say that again.
Well, there's triangulation,
Yes.
and then there's the way the GPS work, which is called trilateration. They're different.
Yeah.
You probably want to try, for what you're trying to do, I think trilateration is a better technique than triangulation. But it's something to think about. So if you want to know about it, just Google how does GPS work.
Okay. Anyway, what I did is I have two markers, and what I've been doing is pushing the platform along to see the top one. The top traces, the red is y, which is the distance from perpendicular to the plane of the two markers. The green is an average of that, so it smooths it out a little. And the bottom is the
average, a moving average, or just an average?
Yeah, it's an average of 5.
Okay.
5 of the values, so it smooths it out a little bit. So if I pull along it's a little difficult to do, but if I pull it parallel to the plane that the two markers are in, the line and the bottom line will change, because the bottom line is the X value from the one marker. So if I go ahead and pull this forward now, not pulling it straight enough. Anyway, the two values change, and I can, basically see that it's giving me valid data, because I can measure, how far it's traveled from the one marker, or the bottom value, the X, and the Y, whether I stay parallel to it or not. And so I can use the Y value basically as, the correct heading, or where, heading, I guess, is where I'm going.
So Ray, that graph, you weren't moving it, right? And so all of the jumping around was noise?
Yeah. I'm assuming I've got compact fluorescent lights in here, and they flash quite a bit, and the targets that I have they're orange sheets of construction paper, so they're pretty big. Yeah. And you get it actually reflects on the floor here, and the floor is it's like a brown bamboo,
Yeah.
And it picks up like orange hues out of the bamboo. So it's, I'm hoping once I get it outside with the green grass, there's no, none of this stuff going on. So yeah, so the values bounce around a little.
So it's going to get better in real life, right?
I'm hoping so, but maybe falsely. I don't know.
That's cool though. That's a lot of progress. It's really neat.
Yeah. So it was.
Yeah.
Kind of a.
Man, it's starting to come along, isn't it?
Yeah. So soon, maybe I'll be mowing with it. But
Yeah,
grass needs cutting, so I have to mow sooner or later. So.
I'm a bit jealous of your IDE. Is there something like that for the Raspberry Pi where I can get graphs easily off the data?
I don't know. I haven't seen one. Has anybody else seen one? Maybe.
I use GNUplot.
Well, it's funny you'd say that because I'm a bit old school like you, because I was going to generate CSV files and then dump them across to GNUplot. Yeah.
Oh well. Yeah. Yep.
There maybe you might check all available. You might want to say real-time graphs /Python on search, and you might. I can't imagine Python's got so many different libraries. I wouldn't be surprised at all.
So it's a Python GNUplot converter, so it's just a Python library that runs GNUplot.
Yeah.
I couldn't find any like that for the Arduino plugin to VS Code, but what I was going to do was use Node-RED dashboard because they have those graphing widgets built in.
Oh.
Node-RED will do it for you, I think, if you can connect Node-RED to your data stream.
All right.
Cool. That's a really good idea.
On the subject of optical flow, I think we were discussing last time, but I've got this little tiny robot, and I've gone ahead and put an order in for 4 Mecanum wheels and a couple more motors and encoders, and I'm going to convert this into a 4-wheel Mecanum robot. And so that was kind of the optical flow idea for that robot. So I started digging around, and in the Pimoroni breakout garden, which is these little tiny sensors, they have one called a PMW3901, which is a 19 British pound cost optical flow sensor. It gives you only XY. You got to figure your own distance, but it's got 121 frames per second, and for 19 pounds, it looks pretty cheap. So I might give that a try. It's got a minimum distance of 88 millimeters, which for the small robot won't work, but for my bigger robot, it might.
What's the IO? How do you talk to it?
SPI.
SPI.
Yeah, and I looked into the Python library that it comes with, and like I said, it doesn't have anything to do with distance. It just gives you X, Y, and that's it. So if you've got some kind of, like for a robot like mine, I know exactly the distance to the floor. I mean, if you were doing it in a drone, it'd be different. But for a fixed height robot, it's almost perfect, and it's just an easy interface, and you get an X, Y value. So that might work fine.
Mm-hmm. Yeah.
Could you put that URL in the chat?
I can't I will. I actually tell you what, I'll just send it into the email list because I only got one screen on. So
that'll work.
But that sensor is a really common one, Murray. I've found a handful of breakout boards built around that. Some of them have LiDAR built into it. One of them is made by a place called BitCraze out of Sweden, and they kind of. I asked about using it on a something close to the floor, right, versus a drone, and they didn't say you couldn't, but they weren't too positive on it. So it'll be very interesting to hear how your results go with it, whether you can find the right optics, right, to get it close enough to the hyperfocal range of the lens that it works.
It says its minimum is 88 millimeters, and my robot's platform is actually 93 millimeters above the ground. So what I've done is I've sent into the Pimoroni forum a question asking, if you're that close to the low range of the optics, does it start to fail or does it still work?
Cool.
No response yet.
Pins and needles. I can't wait to hear what you got because I want to do it.
One more of my many projects, but yeah.
There's never enough.
Yeah, but this is my next one, is that besides the PID controller for my bigger robot, I've got a couple orders in the post now for all those Mecanum, and making this the small 4-wheel Mecanum robot would be lots of fun.
You got some mechatronics ahead of you.
Yeah, big time.
Well, cool. I think we've lost Jack. We've gone a half an hour over, but we've had a good time. Did we miss anybody? Is there anything else we should squeeze in here before we call it a night? Or an afternoon, as the case may be.
The sun is coming in my window right now.
Time to go out and social distance.
Yeah, I'm gonna go up and hang out on the cliff. I've got a 5 or 6 or 7 minute walk up to a cliffside where I can look out over to Kapiti Island across the sea. So that's my goal.
Nice. Don't jump.
Cool.
So how are the corona cases going in New Zealand?
Well, you probably followed the news where we're all very proud of our prime minister because it's actually going really well. We're looking at next week. They've kind of misrepresented it in the news. We're not going off of lockdown, but they've defined 4 levels, and we're currently at level 4, which basically means sit in the toilet and don't leave. But so we can't do anything hardly. But next week, next Tuesday, I think we go to level 3 with restrictions, which means they're going to open more of the businesses that are currently closed. We're still supposed to maintain social distance, but Coastal Fasteners, where I get all my stainless steel nuts and bolts, is going to be open. So yeah.
Robot partners.
So when you say social distance, are you saying like they open the trunk and they'll throw it in the car, or what?
Well, Coastal Fasteners in an email said they're going to be open, so they've got a bench you walk up to and you hand them money and they hand you parts. So I think that means open.
Yeah.
Or
yeah. But yeah, we don't say 6 feet here. It's 2 meters, but yeah.
2 meters.
Okay, well, 2 meters, yeah.
A little better than 6 feet, right?
Yeah.
Huh. That's interesting. A lot of
So snap a picture when you go out over the ocean. I'll be curious.
Tell you what, I'll post to the group a photograph of what it looks like up there.
nice.
Okay.
That'd be great.
That'd be nice.
Great. Do that.
Beautiful countryside, I'm sure.
Yeah, it is.
hard to take a bad picture.
Well, thanks, all. It was a good time.
Yep.
Okay.
That was good. We'll put you on
Good night.
time.
Afternoon.
And I'll remember to stop recording this time. Bye.
Okay.
Bye, all.
See ya.
Bye, y'all.
Bye.
Take care.